Great. Yeah, to Lev, I think you can start sharing your slides, and then we're very excited to have Lev Looney presenting today. Lev is currently a PhD student in meteorology and physical oceanography at University of Miami and works closely with NOAA AOML. And today I'll talk about observing tropical cyclones with Saildrones and the need for collaboration amongst in situ and satellite communities. They mentioned that it's a very busy time for him, given the weather events. So go ahead and we'll look forward to the discussion afterwards.
Awesome. Thank you so much. Please let me know at any point if you cannot hear me or if things on my slides are not progressing, but it seems like they should be.
Yep,
sweet. Thanks.
For now.
Yeah. So good morning or good afternoon, I guess, depending on where you are, as Mara thankfully introduced me. Yeah, my name is Lev Looney. Today I'll be talking a little bit about observing extremes with Saildrones and the need for collaboration amongst in situ and satellite or remote sensing communities. So here, kind of on this intro slide, we just see a Saildrone out in a nice calm ocean. Essentially, this is not what I'm going to be talking about. It's not a calm ocean. It's kind of the exact opposite. But really, before we dive into it, what is a Saildrone? So it is an uncrewed surface vehicle. So it's remotely operated. It's about 23 feet long, sticks out about 10 feet tall above the water. You can see a picture of me standing next to one on the right. And on the left, you can see the sensors it has on board. It's got a variety of sensors to measure things at the air-sea interface, including ocean temperature, air temperature, humidity, wind, wave height, period. And it's also got SST, sea surface salinity, and an ADCP on board to get upper ocean currents. And the goal is to send these into the most extreme environments to collect information about what's happening at the air-sea interface. And this is all part of a bigger picture of observing systems to improve hurricane prediction, where the goal is to get kind of this picture, this graphic, to become a reality, where we get observations from space through satellites, in the air through crewed aircraft, aerial drones and drop sons, to the surface with uncrewed surface vehicles, moored buoys, and down to below the surface with floats, gliders, and other things. So I'm really going to just focus today a little bit on this middle piece, the USVs, the Saildrones. So like I said, we're trying to get these into hurricanes to measure what's going on at the air-sea interface. And so what this slide shows is the tracks from 2021, 2022, and 2023 in blue, green, and orange respectively. I do not have 2024 in there because it is a rather busy time of year. We still are ongoing, and if I'm being upfront and honest with everybody, the Hurricane Helene last week was rather busy and was very unfortunate with the impacts it had, but I did not have time to run the code to update everything for today. But we can see that we're really trying to get these areas where these storms happen. So how do we do? If we overlay all TC tracks over these 3 years that passed within 250 kilometers of a Saildrone, we have about 36 Saildrone TC intercepts within 250 kilometers. Some notable ones from 2021 was Hurricane Sam, where we got within 31 kilometers of the center, measuring a sustained wind speed of almost 80 knots. Hurricane Idalia in 2023, where we got within 11 kilometers of the center, measuring sustained wind speeds of 70 knots. In 2022, Hurricane Fiona, we had 3 Saildrones intercept Hurricane Fiona, closest getting within 4 kilometers of the center and the max sustained wind speed of 68 knots. And Hurricane Lee was kind of our largest intercept in terms of 6 Saildrones. This was in 2023, measuring a max sustained wind speed of 68 knots. And so it's great to collect all these measurements, but it leads to kind of the initial motivation behind part of my project. Do we trust the measurements? Short answer is yes, we do, but we need to show it, especially in extremes. So here's an animation, and when I push play, on the left, you'll see the infrared kind of tracking where the storm is. You'll see a few different triangles. Those are the different Saildrones. And on the right, you'll see a couple key variables, the time series: sea level pressure, temperature, sea surface temperature, horizontal wind speeds, and significant wave height. So as I push play, you can see that once vehicle hit it, and then as we get closer, a lot more vehicles started to come in. But with this blue, if I pause it right here, you see that unfortunately the wind speeds on the cyan stopped. The vehicle experienced, unfortunately, some damage and stopped recording winds at that point. And we can see that here with the pressure, it jumps up. It ended up reading about 1,500 millibars, which we knew was not realistic. but we need to show and kind of quantitatively prove that the rest of these values are. So I'll continue the animation on. The blue one also experienced some damage, unfortunately, but Hurricane Lee was kind of the worst case scenario for vehicle survivability because it was a massive, strong, and slow-moving storm. And so kind of one of the things that I'm going to do is try to prove that we can trust these measurements. But while doing so, I'm going to list some of the challenges as well and kind of talk about the comparisons between satellite observations and in situ. And so what this shows is in order to validate these measurements, we try to compare with other observing systems at the surface. And so this is just a map showing the Saildrone tracks in red and a variety of other platforms in different colors. And the gray dots are the specific storms for 2023. And it's a chaotic figure. And that's kind of the point. There's a lot of coordination. In fact, that first figure I showed of all the different observing assets, that's part of a campaign called the Coordinated Hurricane Atmosphere Ocean Sampling Campaign, or CHAOS. And so it kind of fits well with how chaotic this figure is. And so just taking moorings and comparing to Saildrones. So on the x-axis here, we have the Saildrone observations. On the y-axis, we have the mooring observations. And the color shows the distance apart, and the red line is the 1 = 1, or the line of perfect fit. So how close do we need to be able to correctly compare observations, in situ observations? Well, if we use 1 kilometer, that's great, it's close, it looks awesome, but it really limits data. You have to be, 1 kilometer is difficult to get into, especially in these systems. So what if we go a little further to expand our data set, say 100 kilometers? Well, that's clearly too far. It does not look too good. So what about 10 kilometers? Is that good enough? Maybe. But this also leads to some interesting things. You see a few places where the dots go far from that center line. I'm going to start with pressure because that's probably the most interesting one, and dive into that, and then we'll jump to some of the others. And so when comparing pressure, what this figure on the left shows is the Saildrone ID on the x-axis and the mooring ID on the y-axis. So because these are remotely operated, but we can move them and moorings are stuck, we have this great opportunity to take one Saildrone and have it visit multiple moorings. But at the same time, we can also have a single mooring visited by multiple Saildrones. So we can create this big kind of gridded map of Saildrone mooring comparisons. The colors here show the difference in mean pressure between the Saildrone and the moorings, and the size shows the standard deviation. And while this is kind of a complicated figure, if you just take one row, say this row with mooring 41052, and we move across, the colors stay pretty consistent. So regardless of what Saildrone visits that mooring, the difference between the pressure of the Saildrone and that mooring is fairly consistent. But if we take a column, say Saildrone 1057, and we go to different moorings, that color changes a lot, kind of giving the idea that maybe it's not the Saildrones that have differences in pressures across, but rather the moorings that all have different pressures. And we can further validate this by comparing to different observing platforms. So here on the left is that comparison between the Saildrone, again on the x-axis. On the y-axis is the platform measurement. The left panel A is with the moorings, B is with surface drifters, C is with ships, and D is with another type of drifters, spotter buoys. And so we see that the drifters look great, the spotter buoys look great. The ships have a little bit of noise, but that's not uncommon. They're volunteer observing systems. But overall, they compare really well, leading to this concern that maybe the Saildrone pressure is good, but the moorings are possibly questionable. And one thing I don't want to have as a takeaway is that moorings are bad, Saildrones are perfect. That's not the goal at all. I'm not trying to say that Saildrones are perfect by any means, and that's part of kind of what my overall message that I'll eventually get to. But there's some other areas of possible concern, right? Here I've circled some areas where sea surface temperature is different, here where relative humidity is different, and here where the air temperature is different. And if we kind of make those same maps, and I'll spare the time, we can find out that, well, it's really one mooring that is causing this difference in air temperature. There is one Saildrone that is causing this difference in relative humidity, and a different mooring that's causing this difference in sea surface temperature. So this gives us a unique way to determine what platforms specifically may have set biases. So if we remove those, It's looking a lot better. Not perfect, because again, we're comparing in situ observations across a range of conditions. We're still possibly up to 10 kilometers apart, so there could still be differences, but it looks a lot better. But this leads to an interesting challenge. What is the truth, right? That's one of the challenges with any remotely sensed observation and in situ is what is the truth? And how do you calibrate or validate remotely sensed observations when you aren't quite sure what the truth could be? If you use moorings, but it turns out that those moorings could be biased, then doesn't that imply that your calibration for your satellite or your remotely sensed observation could also be biased? It's a large challenge, and I don't have an answer. And so that's going to be another kind of theme is I'm going to note a lot of challenges, and I'm going to give possibly some insight into some of the ideas for answers, but I don't have all the answers, and I don't want to pretend like I do. We also compared with the spotter buoys. So here I actually used 100 kilometers apart because I wanted to keep the large significant wave height. So spotter buoys, for those that don't know, are just essentially drifting buoys or drifters, but collect significant wave height, and some of them collect pressure data as well. They also give directional wave spectra. And so here when we compare, we can see that it looks really good, especially along pressure and across the significant wave height. I did do 100 kilometers because I wanted to get these large significant wave heights that were propagating outward from Hurricane Franklin in 2023. When you limit it to 50 or less, you kind of lose that. So noting that we were both the spotter and the Saildrone were both very far from the center of the storm. And this leads to another point. We really want to compare in extremes. And so in order to do extremes, we looked at dropsons. So from 2021 to 2023, NOAA and Air Force aircraft deployed 44 dropsons that splashed down within 50 kilometers of a Saildrone. Most of those, however, were in 2023, thanks to GOMO's Extreme Events program. And so what we see here again is on the x-axis, the different wind speeds and pressure measured by the Saildrone, and on the y-axis is what the dropson measures in terms of wind speed and pressure. Again, that red line is the y equals x line, or the line of perfect fit. Color, again, is distance apart. And there's clearly some dots that are well off that line, where we're seeing very high Saildrone values, but very low dropson values. And this makes sense when you really dig into it. Even if you may be 10 kilometers apart, if the Saildrone's in the eye wall, but the dropson is a center drop, you kind of would expect to see extreme differences in the wind speed and also the pressure. And that's exactly what we're seeing. When looking at each of these individual drops, those are all center drops when the Saildrone is nearing the eye wall. And so this leads to another challenge, the need for tropical cyclone relative position. It doesn't matter how far apart you are necessarily, it's how far apart relative to the storm you are. And using this figure on the right, which is just a high resolution hurricane model, where the star is, say, a Saildrone. If we dropped a dropson, say 50 kilometers apart, but tangential to the wind, so keeping the same storm relative distance, not too bad of a comparison. It's not perfect, right? It would be perfect if the storm was perfectly symmetric, which is seldom the case. But it's not bad. Not nearly as bad as, say, if you went 50 kilometers orthogonal to the wind, where you have now the dropsons in the center and the Saildrones in the eye wall. And so this leads to a good challenge. You need to be able to put everything in storm relative position when you're within a tropical cyclone. But it leads to a new challenge. Where's the center? Maybe it's easy to define in this figure, but it gets difficult. In fact, this was a study done by Nguyen et al. In 2014, where they used 4 different methods to determine the center of a storm. And to the eye, it looks like none of them may have worked too well, but this is at one height. This is 2 kilometers above the surface. But if we jump to 8 kilometers above the surface, and unfortunately the domains for the figure change, so I try to map it, the whole figure itself will move, but it tries to keep everything constant. This is at 8 kilometers. We can kind of see that jump. The center moves, and this is not uncommon. If the storm is tilted, then as you move to a different height, the center of the TC changes. And so when you have remotely sensed observations or satellites looking down from above, where the center may be from above could be totally different from where it is at the surface. And this is just 2 kilometers versus 8 kilometers. Could be even more tilted at the surface. So this leads to another big challenge of how do you define the center and how do you put everything in the storm relative position? Now to one of the biggest challenges. How do you directly compare remotely sensed observations? So in this case, a SAR image here on the left that gives you a great spatial pattern to an in situ observation that lacks in space but has time. So on the left in this SAR image of wind speed, we see that the two different red stars, those are two different Saildrones. So we're going to take the Saildrone up here that's in the higher winds, and we're going to look at the same time series on the right of sustained wind speed in blue and wind gusts in red. This black star, kind of ignore the height of it, it just shows where in time this SAR image was taken. And so this is showing 5 days, a lot of variability. We know that that's not a good comparison. So what if we zoom in? What if we zoom into, say, a 6-hour window? And I strategically chose this one because there's no real mean slope. There's not a mean gradient of where the Saildrone was. It wasn't like it was going through the eyeball. But we see 6 hours, there's still a lot of variability in what the gusts are and what the sustained wind speeds are. Sustained winds move up, vary up to 20 knots, while the gusts vary up to 30 knots. But that's 6 hours, that's still a while. What if we zoom in even more, say an hour? We see still that the gusts are moving up to 30 knots and the sustained are moving up to 20 knots. And so this is a big challenge of how exactly do you choose exactly what point? Is it the closest in time? Is it some type of averaging? How do you compare remotely sensed versus in situ? Right? Is the star just, do we get lucky with this time that it's almost right at the exact height of the gusts? This is a big challenge. But it's not the only challenge. This is just how do you compare the in situ? How do you do the time averaging? But I could ask the same question about the spatial, right? If we take a area and zoom in on this 500-meter resolution, a 3x3 kilometer box, and these colors are not to scale. This is just amplified to show an example. And we put a Saildrone, say it's at this point. What do we compare to? Do you just take the closest point? And what is that? Is that the gust? Is that the sustained wind speed? Do we take the average within 500 meters since it's a 500-meter resolution product? Or do we take the max? Which one's a gust? Which one's a sustained wind speed? Or do we do 3 kilometers? Because at hurricane force conditions, a parcel of wind will move up to 3 kilometers in 1 minute. Do we take the average? Or do we take the max? Which one's a gust? Which one's a sustained? It's a challenge that is really difficult to answer. It's a huge challenge. And so I met with the SAR folks at NESDIS that do this analysis and asked what they think. And their answer at first was, okay, well, the 500-meter resolution product is similar to that of gusts, and the 3-kilometer product is similar to that of sustained wind speeds. But that's flawed by definition, right? If you take an average over 3 kilometers of the 500-meter, that means some points of the 500-meter will be above the 3-kilometer average, and some will be below. But in reality, you'll never have a gust that's lower than the sustained wind speed. It's always going to be above. So do you have to do some type of maxing? So I kind of did every combination of every idea that I just discussed across how you do the time averaging and the spatial averaging just to compare, but I had an idea of what I thought would be best. I wanted to do this 500-meter, maybe the max within 500 meters would be a gust, and then the closest in the 3-kilometer would be the sustained. And so when I did that, so this is comparing the SAR image, and this also, I guess I forgot to mention one other challenge. When the SAR image is taken, say, at 36 seconds after the minute, but the Saildrone is on the minute mark, what do you do? So here I took, for the Saildrone, I took the 1 minute sustained wind speeds within 1 minute of the SAR image and averaged, so up to 2 points and averaged them. And then I compared it to the closest 3-kilometer SAR image. And we see that it's decent. It's not a perfect fit. It's got a correlation coefficient of 0.94, a mean difference of 3 knots plus or minus about 7 knots. Maybe it's high bias. SAR is a little high biased on the more extreme. But there's another challenge here. The Saildrones are measuring at roughly 3.4 meters, but yet the SAR product is an estimate of 10 meters. What is 10 meters? When you're in significant wave heights well over 10 meters, how do you define what that 10-meter is? You can use the core algorithm, but does it do a good job at the more extreme winds? So we also wanted to look at gusts, and we did kind of the similar. We took the max within 1 minute of the adjusted gusts, which is a weird thing to think about. How do you adjust gusts up to 10 meters? Is it done the same way as sustained wind speeds, or does it not feel the effects of friction nearly as much? Versus the max SAR 500 meter SAR, 500 meter resolution SAR within 3 kilometers. And it matches up fairly well. We see a correlation coefficient of 0.98 and a mean difference of 2 knots. But again, this is a challenge. Now, SAR is great because it's high resolution, but it is limited in time, whereas, say, Cygnus has a much lower spatial resolution, but it has possibly a lot more images in time. So if we take the single SAR image of Hurricane Lee, if we take 6 hours window around that, this is what we see for Cygnus. A little bit different. Yes, you get a lot more area covered, but it's very different. You really can't pick up the same thing. That's at 6 hours zoomed in. What if we looked at, say, 24 hours, and we just put the assumption aside that a storm moves any bit in 24 hours, which in the case of Hurricane Helene, it moved pretty much the entire Gulf of Mexico in 24 hours from kind of Key West area up to landfall, if not more. So kind of ignoring that, we still have a tough time depicting with Cygnus what the exact structure is of the winds. But that's not to say Cygnus isn't good, because that's not the point at all. It's just another challenge. And so if we actually take throughout the whole season, 2023 season, and find every point that was within, say, 25 kilometers of a Cygnus point and do a 20-minute Saildrone average, we get this comparison on wind speed on the left. There's another challenge with Cygnus, which is they have a different algorithm for fully developed seas or for young seas. And so I kind of use this threshold that may not be correct, and so I'm happy to get feedback on this, of if the sustained wind speeds are less than 34 knots, call it the fully developed sea, and if it's greater than 34 knots, call it the young sea life. There's also no QC. This is kind of, I will say, in its infancy at best, but we see at the lower wind speeds, it does a great job. And depending on if you use the fully developed seas or the young sea life, for this kind of spot, if you see my mouse, it flips over the line if you switch over to the fully developed seas for these higher wind speeds. But overall, it does a decent job. There's just not that much data that we have at the highest wind speeds. However, one thing that Cygnus does that's unbelievable is in terms of significant wave height. And so this is the comparison with sig wave height. We see a correlation coefficient of 0.97 and a mean difference of 1/10 of a meter, plus or minus 0.3 meters, even up to 10-meter waves. So I've given this presentation to the National Hurricane Center, and this is one of the things they were most excited about, especially in terms of Cygnus, was the sig wave height. So hopefully this leads to some idea that we trust Saildrone measurements. It's just a big challenge on how we compare it. So I wanted to briefly mention 2024 season so far, since we are kind of in the middle of it. We've had a handful of storms this year. We've had Hurricane Beryl early on, reaching Cat 5 status early. We had Hurricane Ernesto, Hurricane Debbie, Hurricane Helene, Hurricane Francine. And of course, there's more on the horizon. This was taken this morning. We've got Tropical Storm Kirk out there. We've got this system in the Gulf of Mexico that's being monitored, and this wave coming off that's already, I believe, Invest 91 by the National Hurricane Center and is given a 90% chance of formation. So it's been an active year thus far, and I wish I had some really cool results to show, but to be honest, it's been really busy, very busy. And so I did pull up some summary numbers, and so I'm never a big fan of slides with just text, but hopefully this one's okay, of 2024 Saildrone hurricanes by the numbers so far. This was as of about yesterday. We've had 10 intercepts across 8 different Saildrones and 4 different tropical cyclones, Hurricanes Beryl, Debbie, Ernesto, and Helene. We've measured a max wind speed, sustained wind speed of 67 knots, max gust of 95 knots, a minimum pressure of 951.8 millibars. All 3 of those last stats were actually from Hurricane Helene in the northeastern Gulf of Mexico, and a max significant wave height of 13.3 meters. This was from Hurricane Ernesto. Overall, we've spent 63 hours in sustained tropical storm force winds, 9.8 hours in 50-knot winds, and 26 minutes in hurricane force sustained winds. And this leads to something that I'm actively working on now. Is it's a challenge to actually observe hurricane force conditions at the surface. We went kind of right through, we've gone through the eye wall of multiple storms and have really not seen that much in terms of the hurricane force sustained winds. As we saw with Hurricane Lee, there's a lot of variability from even within 1 hour of these extreme storms. And so again, I want to bring back to this. This has been a big focus for this year, is the observing systems to improve hurricane prediction. And so we've been trying to make this a reality. And one of the best ways to show that is an animation made by Ido Maza from PMEL showing Hurricane Ernesto. And so what I'll do is I'll push play and I'll talk through it. So you will see some aircraft flying through, all the drop zones. I'll pause it real quick. I did, when I sent Ido all this stuff to put in on this animation, I jokingly said, let me add some satellite values as well and data points, and it would have just been way too much to even show. But as I continue, you see a bunch of gliders in the Caribbean. You see a Saildrone here. So one of the things we were trying to do is coordinate the aircraft to fly over and deploy things over Saildrones and gliders. And so you can see that happening a lot here. As Ernesto moves up, you'll actually see here there's going to end up being kind of a chaotic movement of 3 separate flights. And then this third flight is going to launch 2 small uncrewed aerial system, SUASs, into Ernesto. See another 2 Saildrones, another glider, and then they're going to actually deploy another 2 UAS into Ernesto. And one of the goals, let's see if I can do this properly. Technology, if I can pause it right there. One of the goals for these UASs is to, again, get an idea of the fluxes at the surface. And so at what altitude can you get an estimate of what the fluxes are? And so that's been an ongoing test. We did fly, I think, 7 of them into Hurricane Helene, trying to kind of do a step down descent, starting at up to 1,500 meters and working our way down to typically trying to get below 100 meters to measure a full idea of what the pressure, temperature, humidity, as well as the 3-dimensional winds are. And in terms of Saildrone results from Helene, again, this was last week, and I guess very unfortunate of all the impacts it had. But for me, I was fortunate enough to get to fly as part of the Hurricane Hunters to do some of this SUAS work. And so I got back Friday late night, and seeing as Monday was a great catch-up day of everything, I have not really done any analysis on Hurricane Helene, but there was a cool video from a Saildrone, so I figured at least I can throw that in here. And this is what it looks like at the surface. And this is very interesting, and we have a handful of videos like this because, you know, this webinar is RC fluxes from space. You could see all this white. That's not because the lighting is bad. That's just all the sea spray, all the rain, all the mess that is happening. And you see at the ocean surface, you can get an idea of all the sea spray that's going on. The waves here were 9 meters, significant wave height. We did deploy from the aircraft a wave drifter that measured significant wave height of over 13 meters, which is rather impressive given that it is very near land and rather shallow. But definitely a chaotic mess at the surface, and kind of gives an idea of the challenges. And so one of the last things, I know I have just a handful of minutes left before questions, but I wanted to talk about some of the cool science that's been done and at least hit on it. The first thing is using these Saildrones just kind of qualitatively. For different storms, you have different ocean responses. On the left, you have Saildrone observations from Hurricane Idalia, which was a small and fast-moving storm that was intensifying. Here on the top, you see the wind speeds. You can actually see where we were in the eye of Hurricane Idalia, significant wave height, and the ADCP current response. And with this small, fast, and intensifying storm, you see in the significant wave height this rapid growth in the significant waves, but you also see a rapid decay. Similarly, you see a pretty good ocean response down to about 30 to 40 meters and eventually mixing down to maybe about 50 meters. Now we take kind of a very different storm. Hurricane Lee. It was a large storm. It was slow moving, but it was weakening at the time. Again, we see wind speed at the top. We didn't really make it much into the eye. You can kind of see this dip down where we got close to it. But in terms of significant wave height, you see a very slow onset, but also slow decay of the waves. And so this can have very different meanings in terms of the ocean's response. Also, in terms of the currents, you can see that it mixed down to possibly below 50 meters. Another thing we can look at is within the same storm, so going to Hurricane Ernesto, This is kind of zoomed in where you can see here, this is infrared of Ernesto. Is kind of messy at this point, but you have 1068 that went through the northwestern eye wall. The storm was kind of moving off to the top right. And you have 1031 that went through the northeastern eye wall. So we can look at, within the same storm, different quadrants and compare the ocean's response. So looking at that northwest eye wall, we can see the wind speeds here when we were entered the eye. You can see the SST and pressure and the ocean's current response. So 1068 measured a max sustained winds of 60 knots, gusting 82. We saw a max significant wave height of just under 11 meters. And we saw a pretty significant signature of the cooling, right? 2.8 degrees C. That's an impressive amount of cooling. And we saw a pretty good ocean's response. But notice the color bar here is 1 to 1, negative 1 to 1. I believe it's, meters a second. Now let's look at the northeastern eye wall. 1031 measured a max sustained winds of 67 knots, gusting 94 knots. Significant wave height of 13.3 meters. I'll note over here that with this, the wind speeds, you see it stops. Unfortunately, the vehicle experienced a pretty good roll, and the sonic anemometer did not survive the roll at fast speeds down a wave. But we see a pretty different ocean response. We see a cooling of over 4.5 degrees. Now, if you remember that animation, there was the glider that went through as well, kind of the northern eye, and it kind of saw just shy of a 4-degree cooling. So yes, 2.8 degrees seen in the northwestern eye wall is definitely significant, but it's rather different than 4.5 degrees. It's 4.5 is a pretty substantial response. And you can see even with the same negative 1 to 1 meter a second color bar, how much stronger the ocean's response was to 1031. We can also look at the gust factor, so getting an idea of how you can convert the sustained wind speeds to gusts. And so that's the gust factor. What this black line shows is a moving average of what it is as a function of wind speed, and the different colors show different percentiles. And so it's great to know what the mean gust factor is, but what people really care about is the gustiest gust, not the mean gust. And so that's when you start looking at these higher percentiles, 95th, and you see that it jumps up a pretty high amount to up to 40%. It's almost 20% higher than what the mean is. Of course, we have lower number of data points as we get into more extreme conditions. Another thing relevant to fluxes is the drag coefficient. So this is the next two slides are things Greg Foltz shared with me. This shows the calculated drag coefficient from 2021 to 2023. The y-axis is the drag coefficient. The x-axis is the wind speed in meters a second. And the colors here show the wind wave angle, where the darker blue you get, the more aligned they are. And the bright yellow, the misaligned they are. And so you can start to see that there's this peak in the drag coefficient between 20 and 30 meters a second, and then it starts to drop down and possibly level out. It's a little hard to say once you get into these highest winds. And there's a range of colors, but it's really hard to depict what the main signal is. So you can separate it by saying, okay, here that black line is the moving mean with the standard deviation colored. And in green is when wind wave alignment is within 45 degrees, and red is when it's outside 45 degrees. And the circles are where it's significantly different. So yes, the wind wave alignment may have a substantial impact on the drag coefficient, but it is not the primary reason for this massive peak at 20 to 30 meters a second. And the idea looking at photos from the Saildrones during these times is that around this period is when you get a transition in sea state, when you start to really get breaking waves and a lot of sea spray. One of the other things I'll show is we can look at the biogeochemical response. So here, this is from Hurricane Idalia, where you have the Saildrone wind speeds in blue and the minimum pressure in orange. So you can kind of see right when we went through the eye of Idalia, you can see the ocean's current response, and the black is the derived mixed layer depth dropping down to below 50 meters or deeper than 50 meters. And we could also look at the chlorophyll and O2 amounts. And so this is a study in preparation by McWhorter et al., where what we're seeing is this delayed onset of the chlorophyll and O2 spike, and then this rapid stop of it. And we were looking at it and we thought maybe this is where it left the shelf, but looking at the Saildrone depth, it left the shelf in the Gulf of Mexico after the big drop off. And we compare this Saildrone measurements, which is what you see in blue. The kind of noisy lines here are the 1 minute data. The less noisy blue lines are the 1-day averages, and the red is what was calculated through Nestis as the satellite amounts for that area. And so the top A is chlorophyll, middle is sea surface salinity, and the bottom is sea surface temperature. And so starting on the bottom, you can definitely see that the satellites pick up this cooling, but not to the same magnitude that the in situ gets. And even at the 1-day averages, you start to miss a lot of the noise. Same thing with salinity, and especially with chlorophyll. And so I bring back and kind of round it out with, I mentioned this challenge earlier of how do you directly compare remotely sensed and in situ observations, right? Remotely sensed satellites may get very good spatial coverage, but may not be as great in time. Whereas in situ may be much better in time, but not nearly as great as in space. And so I want to change this. It's still a challenge, definitely, but I rather think of it in a way of use it as an advantage. Satellites may see space really well, but may not do time as well. In situ sees time pretty well, but maybe not nearly as well as space. But combined, you can get a better idea of what's happening, not just in space or not just in time, but both space and time. And so I guess I end it with another slide of just text. That's a call to action. That's in situ and remotely sensed platforms clearly complement each other. Each have their advantages. They also have their disadvantages, but working together, you get more advantages. There's clearly overlap between the two communities with everyone trying to obtain the same general goal, which is to better understand Earth's processes to be able to better forecast, whether that's through initial conditions, understanding the past, or looking at the future. And there's a need to advance collaboration amongst the communities. I listed a lot of challenges here, and I'm sure I'm not the only one that's ever felt those challenges. And I'm sure people have felt those in the past and have ideas to solutions. And so this can be done through consistent and efficient communication. At least that's an idea that I've got. So with that, I'll stop and take any questions and leave with my email. Please don't hesitate to reach out via email, and this video of another Saildrone. This was in 2022 through Hurricane Fiona, where it leads to another challenge of in situ, is that the ocean is a rough place. And so things move around a lot. So it's very difficult to observe there. Thanks.
Okay, thank you so much, Lev. Are there any questions from folks in the audience? Yeah, so I'm still taking in some of what you discussed. I have a few questions Maybe one somewhat technical question to start off with. When you showed the slides with your derived mixed layer depth, how were you deriving the mixed layer depth?
Yeah, let me jump back to this. It's just based on the vertical shear of the horizontal currents.
I see.
And so one of the challenges with the ADCP is it has a max range of really like 80 to 100 meters. And
Great.
so kind of getting it done quantitatively was a challenge because you have to find a certain depth of which you want to ignore because it's at the bottom of that range and has a lot of noise, but you don't want to throw out good data. And so that's another project that's being worked on now is how do we improve our real-time quality QC, QA, QC of the data. So this was a few different ways that I tried to do it, and they were all fairly consistent depending on how you define what your threshold is for that shear.
Yeah, sounds good. I'll pass it on to Megan for the next question.
Okay. Great talk, really exciting. I guess I have two questions. The first is with the gliders, are you trying to target having the gliders beneath, like get all the assets like into the eye wall? Or are you trying to get the gliders to be ahead of the storm so that you can kind of see what the potential might be for, you know, heating up the storm? And then the other, great. Yeah, okay. Go ahead with the answer on that.
Yeah, because I'll probably forget. I don't want to forget it. Yeah. With the second one, but it's a great question, and it's definitely a huge challenge. I'm gonna just throw up this slide that shows all the different platforms and assets is an easy one. But it's a huge challenge because the only project, I guess I'm not heavily involved with the exact operations of the gliders. In theory, the goal would be for the Saildrones to be directly over the gliders ahead of, during, and following the storm. But as we know, we are not at a world where we can perfectly forecast the exact track of storms. It would be great if we were. I'd probably be out of a job, but that would be okay. And so one of the goals for the gliders specifically is to get ahead of the storm and get the idea of what the ocean initial conditions are in advance. And we would love to have the Saildrones over the gliders during that time. It's a big challenge of what are the priorities and what are the goals. For the Saildrones, we want to observe the most extreme conditions, but we can easily leave gliders behind because we can move a lot faster than gliders can. And this was a challenge specifically for Helene because there was a glider moving off the shelf and we were right by it. And we were deciding, should we stay with the glider or should we get into more extreme conditions? And so in theory, it would be great to have these all ahead of, during, and after the storm. But in reality, it's a very difficult thing to do. It's very difficult to coordinate any two platforms, much less two moving platforms that have different primary objectives. But as you know, that's one of the limitations of the Saildrones is they don't get temperature salinity profiles. So it's a challenge.
Very good. I'll hold off on my second question because there's so many other hands, but it was about the relative humidity sensor bias, but I'll wait on that. Thanks.
Sounds good. We can definitely come back to it. Yeah.
Sounds good. Yeah, so I can move on to John.
Yeah, hi Lev, great talk. Really nice stuff. It's a massive data set again, so that's really nice. I had something that piqued my interest was the HCP plots and your mixed layer and the kind of offset between the mixed layer and below, especially just after the storm hits, because you can see it kind of sets off this inertial oscillation feature or pattern, which is offset between the mixed layer and below, as I said. But later in the time series, they kind of seem to align again. I just thought that was interesting, and if you have a comment on that.
Yeah, so this is definitely a good question because I've asked this exact question for kind of explanation, and I see Greg's on here, so I know he's done a great job explaining it to me. So I'm going to try, and then hopefully he can come in and save me if I'm messing up. But it's definitely interesting. I think it has to do with how the current is induced initially. When you get later on, you get more of the background currents, the tides, and everything that's moving throughout the water column. Whereas here you're getting purely the wind-driven inertial currents that are propagating downwards and outwards at the same time. And so it's a difference of the source for those. And that's why it's one of the other challenges is, especially in the Gulf of Mexico region where you have stronger tidal currents, to start to distinguish when the ocean's direct response from the storm dissipates and it's just the background state, especially when they're aligned. Greg, I don't know if you have a correction or if that was good or anything.
Yeah, I was thinking the other plot. You showed another plot of the currents. I think it was the ADCP currents in Hurricane Idalia. And to me, that more clearly showed, yeah, that one, right? Where that seems to show the downward energy propagation, upward phase propagation more clearly than the other one, right? So that's what you'd expect, right? So I don't know. Maybe it's the shallowness of the water where Idalia was in the Eastern Gulf that kind of threw that off. I don't know. Yeah, that's something we're not too sure of. Need to look into.
Thanks. That's a good question. Thanks.
Yeah, thanks. Very nice.
Go ahead, Sarah.
Yeah, well, you're on this plot, and I was really just intrigued about how different Idalia and Lee look here, and wondered how much that's because of the particular locations where you were sampling and how much it's really a difference between the storms? Or is it even possible to tell?
I think it's difficult to tell, and that's kind of where looking at different storms and then looking at the same storm, different quadrants can give you some idea. Adalia and Lee were dramatically different. Adalia, I forgot to say some of the stats. At this time, it was moving at 14 knots forward speed, hurricane winds extended only out 25 miles, and tropical storm 160 miles. Hurricane Lee, however, was moving at 5 knots, so a third the speed. Hurricane force winds extended out 90 miles, and tropical storm force winds extended out 200 miles. And so part of that is just the size and speed that really can drive this difference. It was really interesting to me to see the extreme rapid decay of the waves by Adalia. That you saw this quick spike, that wasn't too surprising, but the very quick decay. It could also be, I think, one of the challenges, as you mentioned, is where they are. You're in the deep open ocean in Lee, but you are on the shelf for Adalia, which definitely plays a role, but it's difficult to exactly say. And that's where increasing the data set will help a lot. Looking at things like Helene, where we had 2 Saildrones go through the northwestern eye wall, but you were, again, in shallow water. And it was an even faster moving storm, where you can start to get an idea of the differences in terms of storms versus location.
Thanks.
Are there other questions or discussion topics from the viewers? If not,
I know Megan had another question.
Oh yeah, Megan has another question. Yeah, so Megan, if you want to ask your other question, yeah, go ahead.
About the relative humidity, you saw a bias where the buoys were higher than the Saildrone relative humidity. And I was just wondering if there's some pattern to this or explanation.
Yeah, there's theories. The relative humidity is probably, out of all the things shown here, is, I could say, probably with the most confidence, the one we are least certain about. So one of the ideas, and in 2023, was they were using not the best mesh filter size. And so the idea is possibly these, and I have to look into this, when the Saildrone is measuring much drier conditions, it could be when following an intercept. And so you could have salt from sea spray getting into it and then essentially drying out and remaining and blocking more moisture from coming in following an intercept, leading to much drier conditions. And the reason I have this idea is in Tropical Storm Philippe, we saw, or one of the storms we saw following the pass, we were still in an area of higher winds, but the relative humidity was reading like 50 to 70%, which is just not going to be the case when you're still in a tropical storm. And it read it for a while. And so that's kind of the ongoing idea. For 2024, we have 2 vehicles that were deployed early on that have the old 10 micron filtered mesh. And we have a bunch more that have the smaller mesh to see if this is the case and try to do some more comparisons. But it's definitely a challenge, and that's kind of the ongoing theory. I think it's something Dong Zhao has been working on a lot on why this could be the case, but it's an open question that we're trying to answer.
Okay. Yeah. That's significant. So we do need to solve that.
Definitely. It is of concern of why we're seeing it, because it looks great. And then it's at some point it doesn't. But hopefully after this season, when I get some time, I can do some more analysis and see if there's a look pre-intercepting storm following and post-intercepting storm. And if that bias is only present following an intercept, then that kind of gives more confidence in the answer and the assumption. But it's definitely interesting to say the least.
I see a
Thanks.
question.
Yeah, I was going to follow up on this. Relative humidity is obviously an important variable to capture, but it's also one of the hardest in those kind of conditions. So we spent quite a bit of time on this, and the things that that we found is obviously using a proper filter is very important, but also calibration. They get out of calibration very quickly, and I would highly recommend you talk to Saildrone about calibration, before and after experiment, because we really saw a big difference. So
Thank you.
it's a hard measurement.
Yeah, we try to do some pre-deployment comparisons or pre-mission comparisons, and we try to find moorings that have RH to see how it does. But even before then, before the vehicle's deployed and after, I know we've discussed with Saildrone, even the barometers, we found out sometimes they weren't calibrated as often as we would like them to be. And I think that's one of the challenges of working possibly with private companies, is what they're looking for at the end of the day is money, and trying to figure out the exact calibration, and doing that is not as easy necessarily, but is, like you said, very important to do.
Yes, the only way we had reasonable results was to do calibration before and after in environmental chamber. The atmospheric temperature is okay. It's really humidity that is a challenge.
Yeah, and I should note here that because there were some differences in atmospheric temperature, when I compare the relative humidity, I only do it for times that the air temperature between the mooring and the Saildrone are very close. I can't remember the exact threshold I use off the top of my head, but because the moorings give a dew point and not a relative humidity, I only use times that the air temperatures were similar to ensure that wasn't where the bias lied, was an air temperature. So it was not, and it definitely is something that is difficult. But as you mentioned, and I mean, I think it's pretty clear in the video, if I find that slide ever, is it's a complicated environment, and kind of getting an idea of what the actual relative humidity is and blocking out all the salt from the sea spray is definitely a challenge. And that would be one thing we would love to get in the future, is an idea of how much ocean's in the atmosphere as a measure of sea spray, but also how much atmosphere is in the ocean in terms of the bubbles. But it's a challenge, to say the least.
So we have, I'll talk to you offline. We have a methodology to waterproof sensors for wet gliders, and we've shared it all over the place. But there is, if an instrument capsizes, there is a recovery time. It takes some time, several minutes, 5, 10, 20 minutes for the sensor to get back to functional. But yeah, I'm happy to share that with you.
Awesome. Thanks. Yeah, we can definitely talk offline more.
Good, Sarah.
Yeah, I guess you really nicely laid out the challenges of trying to match different types of observations and matching temporal and spatial scales. It's sort of this thorny question. You showed, I think, winds from SAR and winds from Cygnus. And I guess I wondered, you could also potentially take winds from passive microwave systems or from scatterometer, and they all have different footprints. And I'm sort of wondering if those footprints in the satellite products might provide any window into this thornier challenge you've identified of just trying to match time and space scales.
Definitely. I could not agree more. I think the challenge has been time, trying to get it done. But that is definitely on my radar, is to do microwave winds, but also kind of ASCAT. And I know Nestis I've talked with Zorana, getting the ultra high resolution ASCAT to do some comparisons and really look at all the different remotely sensed winds. One of the ones I did not show specifically, that's totally different because it's not satellite and it's not from space, but it's still remotely sensed, are things like SFMR and IRAP from the NOAA P3 aircraft. So really focused on in storm. And we've been working with Nestis that the Saildrone wind speeds are put in typically to their comparisons. And so far, just to the eye, they look awesome. Compared to IRAP, SFMR has its own issues that I'm not going to get into. But definitely looking at a variety of different products that have different spatial and temporal resolutions is one way to start to get an idea of this. But it's a challenge. And one of the biggest challenges, and I think it was clear in the video as well, is you could see the Saildrones rocking and rolling all over the place. That 10 meters is some threshold that's defined, some number that you have to convert everything to. But how you do that exactly, especially when you're in things like the wave boundary layer, is not defined well and not as clear. And so it's a huge challenge.
You could argue that 10 meters is an artifact of an old-fashioned way of observing, and that when we measure predominantly from satellite and predominantly by looking at surface capillary small gravity waves, that we should be talking about something completely different. But that's a separate community discussion.
Yep, I agree. And I've asked a bunch of people, what is 10 meters? Is it 10 meters above mean sea level? Is it 10 meters above the mean high or high tide? Is it 10 meters above the exact waves? Especially if the answer is mean sea level and you're in waves of 15 meters, then at times, by definition, your wind would be 0 because you're below the surface of the ocean. But we know that's not the case. And so, yeah, that 10 meter number is very interesting. And it kind of also leads to the challenge of observing what maybe the National Hurricane Center is advising, because their winds, their intensity is based off this 10 meter, 1 minute unobstructed average, essentially, of winds. Where in reality do you have 10 meters unobstructed 1 minute? It's difficult. So it's a unique bit, and that's one of the things I'm working on now, is looking at SAR imagery and simulating Saildrone and dropsondes to get an idea of what are the error bars for these comparisons as a function of storm location, intensity, size, all of that. Because I feel my initial assumption is going to be it's pretty large. You have to be really close because there's a lot of noise in these systems, and we see it with the 1 hourly or the 1 hour of 1 minute winds. You see it especially when you look at the higher resolution winds, and you also see it in some of these large eddy simulation models. The amount of noise that you can see just within 1 minute. It's a challenge, to say the least.
Maybe in the last minute, I have a related follow-up question, which is that you mentioned that you're rarely measuring hurricane force winds, even when you're in these hurricanes. And I was wondering if that is related to the fact that your observations are in the boundary layers, or if you have other thoughts on why you're so rarely measuring this hurricane force winds.
Yeah, I think it's difficult to get it. I mean, it's not that it's rare, it's just very difficult. We had 23 minutes of hurricane force from Helene from one of the vehicles. I think it's those areas of the strongest winds can be isolated to certain areas, and those are typically the hardest places to get the vehicles to, just because that's how it works out.
Yeah.
I think the other thing is all those numbers, all the winds that we're looking at are the raw winds. So it's at 3.4 roughly meters. And so if you use any adjustment up to 10 meters, that would increase in theory to be higher. But it's definitely a challenge. I think you have essentially one line in time, and you're getting moved around, and it's just a difficult thing, and we see a lot of noise. So even if you get 5 minutes, that's only 5 minutes of 1 minute sustained winds, even though you went through an eye wall that should have been much higher. And so there's also some stuff with the Hurricane Center that a lot of the times in terms of observations, their intensities compare better with gusts than with sustained wind speeds. And so we see a lot more with the gusts, I think, just in terms of, 9.5 hours versus 26 minutes for 2024. So.
Great. Well, thank you very much. Let's thank Lev again for a really nice talk. And so next week we'll have another webinar, I think at the same time, with Bakemankin on unveiling the pivotal influence of sea spray heat fluxes and hurricane rapid intensification. So hopefully we'll continue some of these related discussions next week as well.